I'll just redraw the phase line, okay, which is given by this. So we have -1, 0, 1, and 2. Okay, so we have the circles here at -1, 1, and 2. These are the roots. Okay, and then we had our arrow pointing this way for that interval, this way, and this way, and this way. Okay, so this is what it looks like basically. I'll try making those bold so we can see them in there. All right, so the thing is that at each of these points, these are all of these roots here where you see a dot, they're all called equilibrium points or equilibrium solutions, right? Because all of these make our y prime equal to 0. So this is when we have our equilibrium solutions or equilibrium points, okay? And then on all of these other intervals, then we have non-equilibrium solutions. So we just have to see, okay, which way is it heading? Which way is our graph tending towards, or how is it behaving, okay? So when we look at these solutions, we actually have a few different classifications of them, okay? So let's say we have a solution that looks like this, where both arrows are pointing in, okay? Or toward that point. Then this is what's called an asymptotically stable equilibrium point. So the way you spell this is like you're spelling asymptote, but asymptotically stable equilibrium point. Equilibrium point. Okay? So then this is the only time we have an asymptotically stable equilibrium point. Only when both of the arrows are pointing inwards. So on our phase line here, we see that this one here is not, no, they're both pointing out. This one here, they're both pointing in, right? Both this arrow here on the left and both this arrow here on the right. So then we can fill that bubble in. We'll fill that dot in, okay? Alrighty, and then for all the other three versions, so let's say we have one pointing in and the other pointing out, okay? Let's say they're doing the same thing but going the opposite way, one pointing in, one pointing out, and also when we have both of them, both arrows pointing away from that equilibrium point, all three of these are called unstable, okay? They're all unstable, but they're still equilibrium points nonetheless. But these are just unstable ones, okay? Such as these ones here, because this one's pointing away, and then these ones are also pointing away. Alrighty? So this would be a stable one here. This would be unstable, and this one would be unstable as well. Okay, so now on the next slide, I'll show you how to finish off this problem. So the final step is to draw the solutions. So draw/sketch your solutions. Sketch the solutions, or the solution curves, okay? So what we're going to do is take our phase line, or our graph, and translate it to the ty plane, okay? So again, here is our function, or our equation. Y prime is equal to f of y, some function of y, which is equal to y plus 1 times y minus 1 times y minus a 2, okay? And then, so again, here, I'm just going to redraw really quickly our f of y, which is y prime, versus y graph. So we had -1 here, +1, +2, and our graph looked like this. And I'll fill that in. It's our S, right? So it looked like this. And then we had our arrows pointing this way, this way, this way, and that way. Okay, so this was the only asymptotically stable one at y equals 1, okay? So the way you translate this to the other graph, so we're going to have y versus t, right? So now we have 1, 2, -1, 2, -1, 2, and 1, 2. Okay, so this is positive, positive, negative, and negative. So the first thing that we're going to do is actually just draw open dots or open points at each of these y values. So -1, 1, and 2. And make sure you do it on the y-axis, okay? So -1 here, 1, and 2. And then what we're going to do is just fill in, corresponding to your phase line here, fill in the dots that need to be filled in. So in my case, or in this case, we're going to fill in the +1, 1. Okay, and then we're just going to draw horizontal lines through each of those points. Horizontal lines through each of those dots that we just drew, okay? And reason being is because, remember we said these equilibrium points are when our slope is 0, when our y prime is 0. So all the way across, our slope is going to be 0, okay? So that's like kind of formulating or drawing the grid for our graph here. And then what we're going to do is look at the arrows, okay? So beneath -1, so from here on that way, when y is less than -1, then that means y is decreasing, okay? So here's -1, this line here, y is equal to -1. And then, so once we're going from left to right on our t, then y is decreasing. So that means it's dropping down and down and down, okay? And you can always draw arrows to denote which way your graph is traveling, okay? So it's going down like that. And then here's our y equals 1 line and y equals 2 line. Okay, now we look at this arrow in here. So now we're looking at this interval, all right, from -1 up to 1. Then we see that the arrow is pointing upward. So that means that it's going from this equilibrium point, or line, all the way up to, and it's nearing the other equilibrium point, okay? So it's going this way, all right? So that takes care of that interval. Now we'll take care of our interval from 1 to 2 on the y. So then we have, well, now it's going down this way. So y is decreasing from y equals 2 down to y equals 1. And it's nearing that line instead. So it's going toward our y equals 1 line, right? And then the last interval is just going to be from 2 and above. And that is y is increasing. So it starts at 2, but then it starts increasing all the way up to infinity, right? So this is what our graph looks like. And also our solution curves, there doesn't only have to be one in each like region kind of thing. So you could draw some more in here if you want to make it look like water flowing kind of. But only one is usually required, okay? So that is how you graph and how you analyze qualitatively, an autonomous equation, okay?